Hi, my name is Artit Wang Per Wong, and here I will discuss cross-lingual language model pre-training. This is a dissection and review of the original XLM paper that was published by Facebook researchers in 2019. The outline of this presentation will cover the motivation behind XLM, tokenization, subword tokenization, byte pair encoding, zero-shot translation, autoencoding pre-training, and autoregressive pre-training, the XLM model itself, XLM models actually, and the differences between XLM and XLM-R, and finally a comparison of different pre-training transformers. So the motivation for XLM. Firstly, there's one model to learn them all, meaning there's a model for all of the languages, and a pro of this is that there's no need for a new model for each language pair that we want to translate between. A con of this could potentially be that you need a larger model overall than a separate language pair model. And this could lead to either higher inference time or more computational requirements for training or inferencing, or both. The second motivation is zero-shot or few-shot translation. As we will discuss later, a cross-lingual model allows us to have high-quality translations for low or no resource languages. So essentially, languages with very little data, especially for translation. Cross-lingual language models will allow us to not only translate between them better, but also model the language better itself. Finally, number 3, pre-training both the encoder and decoder. This is important because, as we will cover, the vanilla transformer that has really given a lot of stride to advances in natural language processing, especially machine learning, machine translation, the vanilla transformer was not provided pre-trained. Later on, we had BERT in 2018, which is based on the encoder part of the transformer, and that is a pre-trained model. And then we also have GPT, which is based on the decoder part of the transformer. And why is pre-training important? Pre-training is important because it allows us to train a model with a lot of data and to transfer that learning, either through transfer learning or fine-tuning, to other downstream tasks. So for instance, let's say we pre-train a language model. We can use that language model for named entity recognition, or part of speech tagging, or text classification. So pre-training models are very useful for a variety of purposes. On the image on the right here, we have the vanilla transformer, which was published by Google researchers in 2017. This vanilla transformer consists of the left portion here, which is the encoder. You have inputs into the encoder from the bottom up, where inputs are turned into an input embedding, and a positional embedding is superimposed on that, and it goes through multi-head attention layers. Several stacks of them are possible, and this encoder connects to the decoder, which is the right side, which also consists of a bunch of multi-head attention layers. And the input to the decoder, it starts with what we want to start the output with, and then there's a mask self-attention, which masks the output so that it's a left to right output scheme. And so the output of the decoder is a linear and softmax layer with output probabilities. And so these two, encoder and decoder, comprise the transformer. And these multi-head attention layer consists of self-attention mechanisms. And self-attention mechanisms are important because it allows each element of a sequence to attend to other elements of that sequence, so that relationships could be established between each element in comparison to all the other elements. Now, this is important because the encoder and decoder of this transformer essentially comprise of a sequence-to-sequence model. Before transformers, a very high-performant models were LSTM models, long short-term memory models. And they are still very good, but transformers has really demonstrated to exceed their performance in many natural language processing tasks. Next, let's talk about tokenization. Now, tokenization is important because it's often a very important part of the pre-training pipeline, and we wouldn't want to have that overlooked. There are different types of tokenization possible. Here I've listed 4. So the first one is word-based tokenization. Essentially, in word-based tokenization, we're splitting by spaces. So let's say you have a phrase like good morning. You would split by space, and you have good and morning as 2 different tokens. And you'd give each token an ID. And then with that, you would train a model based on that. There's also phrase-based tokenization, where you wouldn't split on just the words, you would split on the phrases. So in this case, good morning, if we consider that a phrase, we'd keep that as a single token, and there might be other phrases in the sentence. Number 3, subword tokenization. In this case, we break down a word into chunks or pieces where there are different schemes of how we do subword tokenization, which I will get into. But in this example that I've contrived, good is split between go and od. Morning is split between morn and ing. Okay? And then there's character-based tokenization, where we literally split on the characters. So in each of these types of tokenizations, each token is an element in the sequence. We will mainly focus on subword tokenization because subword tokenization has shown to be very effective in pre-training our models for natural language processing. And the reason why it is so effective, I've listed 3 reasons here, and there are more which we'll cover. The first one on the bottom left is named entities. So between languages that share an alphabet, names can often be copied from the source to the target text. For those that don't share exactly the same alphabet, transcription or transliteration may be required, especially if the alphabets or syllables differ. For example, Barack Obama in English and German is the same thing. In Russian, it's spelled differently, but the form and the sounds are essentially transliterated, the characters, and likewise in Japanese. The second reason in the top right are cognates and loanwords. Cognates and loanwords with a common origin can differ in regular ways between languages, so that character level translation rules are sufficient. In the example here, we have claustrophobia, and in German it's spelled differently, but it's almost the same actually. So if you look at the word as a whole, you might not capture the similarities, but if you break it to the subwords, you would be able to do that in this case. Finally, in the bottom right, morphologically complex words containing multiple morphemes, for instance, via compounding, affixation, or inflection, may be translatable by translating the morphemes separately. As an example, solar system in English is 2 separate words, but in German it's 1 word. So these tokens would not be comparable if we didn't consider subword tokenization in this case, and likewise in Hungarian as shown here. So, subword tokenization. The advantages are, firstly, OOV, out of vocabulary words. When we pre-train a model, we have to build a vocabulary. But when we use that pre-trained model later, it might encounter vocabulary or tokens that were not originally in the pre-training set. So by breaking down the tokens into sub-words, it allows us to have more coverage of out-of-vocabulary words. Again, words that do not appear in the pre-training set. And next, subword tokenization accounts for the internal structure of words, and this is what we covered earlier: names, compounds, cognates, and loanwords. And finally, it allows for a single vocabulary for all languages. We don't have to do this, but it is advantageous for multilingual and cross-lingual pre-training models. Now, popular implementations of subword tokenization include, firstly, BPE, byte pair encoding, and word piece, which is essentially a modified byte pair encoding, which is proprietary training software maintained by Google. Sentence piece, which includes both includes 4 different tokenization schemes: byte pair encoding, unigram, character level, and word options, and this is completely open sourced by Google. When it comes to applications, byte pair encoding has been applied in GPT, XLM, and Roberta. Word piece has been used for BERT, and then sentence piece has been used for XLM-R and MBART. Now let's walk through an example of byte pair encoding. Suppose we wanted to encode the data AAAA, BDAAA, BAC. What we do is we look for the pair of characters that occur most frequently in the data. In this case, AA occurs most often. So we would start building a dictionary, a replacement table, you can also call it that way, of capital Z equals AA, and we'd substitute that into the original data, and you'll see that the data has been compressed, and now we have this sub word token Z, and we can repeat this process. Next, we see that the most frequently occurring pair AB can be replaced with the capital Y. And we can also do this recursively in this last example here, where capital Z, capital Y can be replaced with capital X. And so we have our dictionary, X, Y, Z. These are now the subword tokens for which we will train on. Again, these are the subword tokens that form the sequence of our data. And the data is compressed, hence byte pair encoding began as a compression algorithm, and it was not actually intended to be used for tokenization, but it has been applied in creative ways. So even though I show here that we look at characters, we can actually look at the byte pairs of the characters itself. And by doing that, we can actually better tokenize multiple, like, Unicode characters so that multiple languages can be tokenized. And so that's byte pair encoding. Next, let's talk about zero-shot translation. Zero-shot translation refers to the fact that we can translate between 2 languages even though we don't have that training data, that parallel data between 2 languages to train the system on. What do I mean by that? In this example here, which is published by Google in 2017, using LSTM sequence-to-sequence models, the machine translation system was trained on English to Korean data, and then English to Korean data, and then English to Japanese data. And what was demonstrated was that same system can also translate between Korean and Japanese, even though it wasn't trained on Korean and Japanese language translation. So this is what zero-shot translation refers to. There was 0 data for Korean and Japanese, and it could still translate between the 2. So what is this visualization here? This visualization on the left with a bunch of clusters, each cluster with their color codes represent similar types of sentence meanings. And so let's zoom in on this rightmost cluster here that's red. And as we zoom in, we'll recolor code that with the different languages. And we see that this system that was trained on English and Korean and English and Japanese parallel data is able to cluster sentences with similar meaning of all 3 languages. Hence, this sort of illustrates that it is able to do zero-shot translation between Korean and Japanese. And we'll see that this is an advantage of cross-lingual models, where the sum is really greater than the parts. And by that I mean if you trained separately an English to Korean model and then an English to Japanese model, those are 2 separate models that we wouldn't have been able to use to translate Korean to Japanese. Okay, next. Let's talk about different pre-training styles or pre-training approaches. In the first case, we'll talk about auto-encoding pre-training. And the very common example of this, or popular example that has worked well, is BERT. BERT stands for bidirectional encoder representation from transformers. And the way it works is you start with an an input sentence. In this example, it is my dog is cute. He likes playing. And you can see that playing is, so with subword tokenization, the ing is extracted out as a different token. And we take this input and we add to it first we have the token embeddings after the subword tokenization. We add the segment embeddings. There are two segments, A and B, because there are two sentences, A and B. That's how the model works. And then we add the position embeddings, which indicates which position in the sequence does each token belong to. So this is the input into the model, into BERT, and what BERT does is when it's pre-training, it masks some of these tokens. For instance, it might mask dog. And then the BERT pre-training scheme essentially looks to predict that the masked token was dog. And of course, it masks a random number of these tokens, like for instance, dogs and likes. And so the model is supposed to predict that. Now, this type of pre-training is called autoencoding because we're essentially trying to recreate the input. And so the model is encoding it, it's autoencoding it. It's recreating the input, and the input is corrupt with some noise. Now, BERT also does something extra called NSP, which is this top left indicator here, which stands for next sentence prediction. Next sentence prediction is essentially seeking to predict, did the sentence B occur after sentence A in the training data? And of course, when we're pre-training BERT, we would mix it up. Sometimes it does, sometimes it doesn't, and the point of this, the model is supposed to predict when it does. So this autoencoding method of pre-training works very well, as BERT broken a lot of records and benchmarks in the NLP field. And it will be, as we will see, it will be used in XLM and many other models. Next, let's discuss autoregressive pre-training. Autoregressive pre-training refers to this left to right model, and GPT is a very common or very well-known implementation of an autoregressive pre-training, where what we do is we have a masked self-attention on the decoder side of on the decoder of a transformer, the decoder blocks, and this masked self-attention prevents each token from attending to tokens on the right. So in this example here, we have we're at the token obey, and obey can only attend to the left tokens, which is the start token, robot, and must. And it's looking to predict the next token, which is orders. So this is what autoregressive pre-training refers to. Now, if I go back up to this BERT pre-training method, each token can attend to any of the other tokens on both the left and the right side. Hence, it's bidirectional. But autoregressive pre-training is not bidirectional. It's left to right, as we can see. Finally, how does all of this bring us to XLM? So the original XLM paper describes 3 different pre-training models, actually. Okay, so there are 3 XLM paper, again, is 3 different pre-training models, and we'll compare them, how they work, and decide which one's the best one. And the first pre-training model is the causal language modeling, CLM objective, which is essentially next token prediction. That's like GPT. So CLM is, again, autoregressive training, and one of the languages is selected for each training sample, and we can train it on multiple languages. That's what XLM does. The second type of training objective is the masked language model, NLM objective. This is the BERT-like model. Essentially, it's the autoencoding training. And again, one of the languages is selected for each training sample. Finally, the third is the translation language model, TLM, which is coined originally by this XLM paper. And in this objective is essentially an extension of BERT's MLM to multiple language inputs. This is a combination of MLM and TLM. So this consists of concatenating a sentence in 2 different languages with random masking. And then we have to predict the masked token. The model can use both the surrounding context in language 1 as well as the context given by language 2. So in figure 1 of the original XLM paper shows illustrates those two MLM and TLM language model pre-training schemes. So the top image here, the mass language model MLM, in this case we have a sentence, or a sentence pair. Take a seat, have a drink, now relaxed, and blah blah blah, multiple sentences that are just concatenated together. And then we have position embeddings, which describe their position in the sequence. And then we have the language embeddings, which in this case is English. So this is very much BERT-like, where we mask some of the tokens, we try to predict it in an auto-encoding manner. Then we have the translation language modeling on the bottom here. And in this case, we have English and French input sentences, and this requires parallel data. So in this case, the curtains were blue, and I don't know French, but that's essentially a correct translation of that sentence, and we mask tokens and we have to predict it. So in this case, it has to attend, each mask token has to, the context of surrounding the mask token for both languages have to be considered to successfully be pre-trained in this manner. All right, let's look at table 1, which shows the XNLI benchmark on 15 different languages. So the XNLI is machine translation baselines and zero-shot classification using cross-lingual sentence encoders. So in this case, we're trying to classify the different languages, and if you look at the bottom row here, we'll see that XLM using the MLM and TLM pre-training objective performs the best across the board in comparison to other methods like Devlin et al. 2018. That's the BERT model essentially. Now, the key here is that using the MLM and TLM objective performs the best. Unfortunately, the CLM does not perform as well, and we'll talk about that in more detail in the next tables. So in table 2 here, we show results for unsupervised machine translation. Here are the blue scores. Now what this table does is that it looks at the performance of the encoder and decoder pre-training for XLM. Remember, XLM pre-trains both the encoder and decoder, which is unlike BERT, which is only the encoder, and unlike GPT, which is only the decoder. And what we see here is that EMB is using the lookup table with cross-lingual embeddings. The dash is essentially random initialization of the weights of the model, and CLM is the causal language model, MLM is the mass language model. And if we look at the best numbers, which are in bold, we'll see that for the encoder and the decoder, the MLM objective works the best. And if we mix it any other way, it wouldn't be as good across the board. So this shows that of the different pre-training schemes used in XLM, the mass language model performs the best. Now let's look at table 3. Table 3 is for supervised machine learning, the blue scores, for Romanian to English. Again, the mass language model here with the bold shows the highest performance, really across the board. So the key takeaway is that for XLM, mass language model performs the best. Now let's look at how XLM produces cross-lingual word embeddings. By cross-lingual word embeddings, what I mean is that for a given word in each language, for instance, in this case, cat, and in the different examples, Italian, gatto, and Japanese, I don't know how to say cat in Japanese, but for the same word in these different languages, word embeddings, they should anchor to approximately the same location relatively. And one way of measuring it is to use different similarity scores. So I'll start with table 5 in the lower right here. As we can see in table 5, the first column is a cosine similarity score. So the higher the cosine similarity score, which is essentially a dot product, is, then the closer the word embeddings for the different languages, the better they align. The L2 distance is the distance measure, so the smaller it is, also the better it aligns, which in this case, the XLM does do the best here. And for semi-val uses a Pearson correlation coefficient, and so the higher the correlation coefficient, the better, which in this case it does here too. And sum-eval 17 is another benchmark, but uses the Pearson correlation coefficient. Now, it compares to two other models, Muse, M-U-S-E, and then Concat. So Muse is based on fast text, multilingual word embeddings. So fast text is like word2vec, but trained using subword tokens. And then Concat is also fast text word embeddings, but it's trained by concatenating monolingual corpora from different languages and then training it like that. And so it was shown to do very well for aligning word embeddings from different languages, and XLM has been shown here to do even better. Now, let's look at table 4, where what we want to demonstrate here for low resource languages like Nepali, a cross-lingual model can help. And how is that demonstrated? So in the first row, if we just train a language model with Nepali only, the Nepali perplexity is 157.2. Now, perplexity measures how well a language model performs, essentially how well we can predict the next token in a language model. And Nepali is, again, low resource language, so the perplexity is fairly high. A lower perplexity is better. Now, after we train it with Nepali, if we train it on English data, that perplexity for Nepali goes down. Again, these are trained languages, different languages that are trained on the same cross-lingual model, but there's no parallel data between them. You're just training in Nepali, then you train with English. Now, if you train Nepali and then Hindi, you get an even lower perplexity, because Hindi, based on its Sanskrit, is more closely related to Nepali, so that makes sense. Now, if you train it on all three, Nepali and English and Hindi, the perplexity is even lower. So this table 4 here demonstrates that, again, the sum is really greater than the parts. If you were to train just a Nepali language model, it wouldn't do as good as if you added English and Hindi to it as well, even though, again, you don't have parallel data between those languages. Next, let's talk about XLM and XLM-R. So, XLM is based on the Roberta style of mass language model pre-training, at least for the best performing models, as we saw. Now, XLM-R is based on Roberta style pre-training. What does that mean? Well, after BERT, Facebook researchers looked into improving BERT by removing next sentence prediction, having dynamic masking of tokens instead of masking the tokens in the data prior to training. You mask it while you're getting the examples to train it on, and also byte pair encoding, and training with more data. Roberta, Facebook researchers were able to demonstrate that BERT could be improved in a new pre-training method, which was referred to as Roberta. So more languages with XLM-R, and the language embedding was also removed, and sentence piece unigram tokenization is used, and overall that leads to an even higher performing model than XLM. So if you were to use a model, XLM-R would be the one to use. Finally, let's talk about different pre-training transformers and how do they compare. In this table that I've created here, I show different models that we've covered and some that I will cover next time. So the first model is the BERT model, created at the org Google. Uses word piece tokenization, and it uses an encoder. It pre-trains on the encoder using an autoencoding pre-training strategy. And there are multilingual implementations of BERT called MBERT. GPT, which is from OpenAI, uses the byte pair encoding tokenization and uses the decoder side of the transformer in an autoregressive pre-training fashion. And you haven't found any multilingual implementations of that, but I'm sure it could be done somehow. Then we have XLM, which is what we cover mostly in this presentation, and XLM-R. It's from Facebook. XLM uses byte pair encoding tokenization. XLM-R uses sentence piece unigram tokenization. And it's pre-training both the encoder and the decoder. And what was found was that the autoencoding method of pre-training shows better performance than the autoregressive method of pre-training. And of course, this is a cross-lingual model, so multiple languages are involved. Now, another thing to note is that for classification, the encoder turns out to be the more important part of the encoder-decoder pair, because the encoder really has that, it captures the bidirectionality, remember, of the input sequence, whereas the decoder only does the left to right part, but the decoder allows for autoregressive pre-training, which helps with text generation. Now finally, there's MBART and CRIS, which are even more higher performing models, which push the benchmarks and performance even more. It's also from Facebook. They use the byte pair encoding tokenization. It pre-trains both the encoder and decoder. And the pre-training method involves both autoencoding and autoregressive. Now this is unlike XLM, where we either do autoencoding pre-training or autoregressive pre-training, and then we compare it. This is doing both simultaneously. And I'll cover there next time what that entails and how that makes a better model. Now note that there are many more pre-training models out there, such as XLNet, UniLM, MAS, etc. And we don't have enough time to cover it now, but there's so many models out there with different variations of how they operate and the architectures, and so it's good to really have some way of comparing and laying them out here, which is what I've tried to do in this table. So with that, if you have any questions or suggestions, please feel free to contact me, rtw@facebook.com. Thank you.